you should have asked me what type of pile are you talking about, because there are many different piles. You can have purely end-bearing pile. Say you're having very soft clay and then sand below. You basically design them as purely end-bearing. You can have the opposite case where you have simply only friction, because there is no stiff layer or bedrock. Then you have to design the piles to carry everything more or less as skin friction, especially for piles like in Kandla port and so on, where the stiff layers are really, really deep. You basically make the piles big and get the skin friction there. Sometimes piles are also not used for load carrying at all. You just use the piles as a means of ground improvement. You can have these compaction piles where you drive a lot of them in close proximity so that you jack up the horizontal stresses and therefore make the ground stronger due to compaction. Uh, when you do this, it's important you realize that it's not so much the volume change causing densification. That's the big contributor. It's actually the horizontal stresses increasing that gives you the ground improvement. Because your horizontal stresses go up, your mean confining pressure goes up, and therefore the strength of the material goes up. It's not just the densification that causes the issue. Uh, you can have these onshore tension piles, and these are getting quite more common these days, where you have to have the piles designed for taking both compression and tension. A typical example could be piles on either end of a raft, where you get rocking of the structure will induce axial tension in one of the piles in any half cycle. Under dynamic loads, this is quite possible. The other application where you can get tension in your piles is if you look at the station box they constructed in Canary Wharf in London. The whole station box is below water. It's next to the wharf, obviously. Therefore, the only way they could keep the station box below water is by having piles underneath, which are the box wants to float up, and the piles are holding it down. So they're all tension piles. So there are more applications of anchoring structures to the ground and stopping them from moving upwards is a common application these days. And of course, on offshore, we got many examples, but one common use is as a pure tension pile where you want to moor something to the seabed. So this is quite common use. So there are many, many different types of piles depending on what they're used for and what function they're serving. Now, I got this set up at our university lecture page, which means this is the slide you get and you can ask questions straight away. Static design is normally you're designing the piles to carry the vertical load into the soil. The horizontal loading part we will do separately later on. As I said earlier, we tend to use quite a large factor of safety for pile design. Between 2 and 3 is quite common. So all of us, we've done this already. So the carrying capacity, ultimate capacity of the pile comes from the base capacity and the shaft capacity. And base capacity you can work out using this equation where NQ is your bearing capacity factor, as somebody said. This was done by percentile back in 60s. And this NQ factor changes dramatically, as you can see, with the friction angle. So if you make an estimate of 35, you get about 60. If you made it about 38, you get about 100. So you can see at least whether this equation, this graph is right or not. What it is saying is that it's important that you estimate your friction angle reasonably well, because you can overestimate or underestimate your base capacity by factors of 10 easily. So if you're too conservative and said, oh, I can't be sure, and maybe my friction angle is as low as 25 degrees, then you end up with an NQ of only 15. Whereas your real soil, you design this, give it to your pile driving contractor, and they can't put the pile in the first place, they'll come and blame you. What kind of engineer are you? You know, you said that you need such long piles, and we can't go. They reached what they call the refusal depth quite quickly. So you lose fits. So don't do that. Have a good estimate of the material problem. And as you guys were saying earlier, the traditional way, maybe following prompts or somebody like that, is you estimate your shear stress based on this KS factor, sigma dash V and tandem W. We've written that already, which is good. Now, the interface friction is an important parameter in this, which goes from, for steel, using something like 20 degrees is probably reasonable because there is enough experimental evidence also to look at the interface shearing between steel and soil, and that's not far off. Concrete, people use 0.75 of phi dash on the understanding that it's not so much the interface friction that governs it. If you have a concrete pile, you expect the surface to be like that, jagged, and the sand will probably go, or the soil will go in there, and that's my pile. And if I apply the load, the shearing will happen not there, but maybe a little bit away from the interface. So you got some interlocked particles in there, but it will soon find a surface on which it can shear. And that's why you reduce your friction angle by that by a little bit, maybe 3/4 of that, and expect the shear plane to be a little bit further away. Wood is even more warpy, and people are unsure. That's why you got a lower factor of 0.66. And in any case, there are not that many wooden piles being used around the world anymore. And then you adjust your KS factor according to relative density. These are very simple Tomlinson style calculations. So they give you an answer. They're good to pass exams, but when you actually design these things and it costs you real money to build them, you will very soon realize they're not so good. The idea is that, okay, you work out the shear stress, but at least you should be able to integrate that along the length of the pile, so that you got this your surface area 2 pi r times the integral of the shear stress along the length, which makes perfect mathematical sense. But if you can't do the integral, or if there are many layers, then you need to do this by integration is basically summation. So you can divide that into many layers and work the properties for each layer, and you get a better estimate. Now, let's go away from that kind of traditional design, and let's see how else can we design piles. And most of the stuff I'm talking about is actually in Mark Randall's ranking lecture, which you can really download and read, I'm sure. Mark spent all his life looking at piles. So if he says something about them, he probably thought about it quite carefully. The basic idea of designing piles based on CPT is quite a sound, philosophically it is quite sound. Why? After all, when you're pushing a CPT into the ground, it is like a mini pile. So if you're measuring the resistance on the mini pile, all you then need to work out is how to scale that to a bigger pile. That's all we need to do. So it makes sense inherently that we use CPT. And this is why I push for CPT rather than SPT, because CPT should mimic the same mechanism, flow mechanism, as you're driving the pile. You will get the same thing as this, for which we have solutions. And I got this off the website from somewhere. Typically, this is what you will get. You got your cone resistance, usually in the orders of megapascals, cone dip resistance. You can get also, if you, depending on your cone, a pressure measurement, water pressure, so you call the piezo cones, and you can get a measure of the sleeve resistance as well. So you can somehow identify the difference between the cone tip resistance and the shaft friction. And they do that by having two parts to the cone. Uh, and quite useful for pile design, because if my cone is like that, and I have a sleeve on this, which is measuring the friction along here, and obviously you need a contraption to carry the load to measure from there. But you can measure the water pressure here, the QC there, and the sleeve. And most companies, like Keller, if you ask them nicely, they'll give you all the three of those parameters. So QC with depth, sleeve resistance with depth, and pore pressure with depth. I'm only showing you the QC part here. And of course, when you do this cone, you don't push it at just one location. You've got the truck, you may as well drive it around the site and push it at several locations. Then you can get some statistically sensible variations with depth. So you can have a mean, you can have a mean minus standard deviation and mean plus standard deviation. So you are more confident about the soil properties with depth. You can also do, for this site, they have done both CPT and SPT, and you get these SPT blow counts, which will be at specific locations, and you can see these numbers. If I showed you this, you will imagine a certain soil profile. If I showed you this, you will imagine something different. And that's the problem. And these both were done exactly at the same site. Okay? So having discrete measurements like the SPT, while in a way better because it's an in situ measurement compared to C5, it's not as great as having a CPT. So let's root for CPT. Now, once you got these, if you follow the work of Robertson and Wright and other people, they have correlations from CPT to everything in the world, including your mother-in-law. So they have a correlation to get the relative density with them. They have a correlation of the CPT to friction angle. And people have made careers, Paul Main and the rest of the lot in the States, basically made a living on doing CPTs and converting them into something they think the industry wants. And you will take them with a pinch of salt, but those correlations exist. And by and large, because there's so much data, you can't be that far wrong. It's not based on just one test. They have done this for years and years. So there are correlations to other things. For this site, what's interesting is, if you look at this part, you're getting some kind of a crustal increase in the cone resistance, and as you go deeper, when you enter these fine sands and silts, you're dropping your cone resistance. Now, if you convert that into friction angles, you can see you can getting something like peak friction angle of nearly 40 degrees here, and it drops to about 30 to 33 here. Now, part of this may be due to pushing the cone too quickly and therefore generating positive pore pressures, especially in fine silts and so on. And this is why doing just the cone resistance is a bit iffy. If you have the pore pressure measurement with this, then that will tell you if the pore pressure is then going up when you enter those layers, then this drop makes sense. What that tells you is the drain parameters are probably quite good. It's just that your cone is being pushed too quickly, you've got pore pressure around it, and you're losing your QC. Okay. So there is a bit of interpretation to be done with the cone test as well. It's not a blind game. Ah. So this is how it's typically done. So you got your truck, you drive to the site, and inside the truck you got your rod and your actuator. And the good thing about this is your truck is your reactant mass. So that's why they lift it. If you see the wheels of this thing, you may have seen a CPT truck. Maybe I'm being, no? Okay, then the picture makes sense. I'm sorry, I had to pitch it at some level. You can see the wheels are off the ground, and that's because the cone is being pushed down and it's reacting against the truck. Okay, so you come off the ground on the jacks, and the entire weight of the truck is then sitting on reacting against the cone, and they push the thing to, in this case, up to 12 meters, but you can push them longer. You keep adding more lengths, and you keep driving them, and you, as I said, you get this tip resistance and also the sleeve resistance here for friction ratio. So clearly, when you have fill, you got small QC. Where you're going through mud, you flatlined. There's no strength to the material. And when you got to silty sand, you picked up nicely, and dense sand, you're off the chaff. Now, once I have this, so I mean, as I said, in the UK, we tend to design board piles more often than not because we can make very quickly a hole in the ground, and the hole stays open because our clay is strong and over consolidated, and we can pour concrete before it caves in. So board piles form about 80 to 90% of the piles in the UK. So it's important for us to estimate the pile capacity for board piles. And Fleming has done this based on this equation here. It's effectively a hyperbolic relationship between the end bearing pressure and the displacement, base displacement. So if I have the ratio of QB to QC, then that's approximately related to the displacements normalized to the diameter. So this expression must be true for both my pile as well as the cone. So any unknowns in this, I will substitute D as the cone rod diameter. So I know D, then I can work out, I know QC, then I can work out what QB is, and then use the factors then to work for the big pile in the design. Make sense? Straightforward enough? So that's one idea. This was back in '92. For driven piles, there are obviously you're going to get more capacity from a driven pile. As I said, it's not so much due to densification you achieve by driving the pile. The extra density you gain because you're pushing the sand or the soil away from the pile volume is marginal. It will increase your friction angle by a small amount. But what it does quite nicely for you is it creates this massive horizontal stresses. Okay? So if you drive the pile in, because of the action of the soil wanting to go there, you must mobilize passive pressures, right? And you know passive pressures can be about a factor of 9 compared to your active pressures if it's frictional soil. So that's quite a big increase. And if I have big horizontal stresses, if I go back to even our basic equation we looked earlier, so this Ks factor will increase enormously because effectively Ks times sigma dash V is my sigma H dash or sigma dash H. That is what's going up. Yeah. So what we are saying is that the increase in horizontal stress or which gets locked into the soil will give you the extra capacity for the pipe. And that's quite significant. Also, you will get this residual pressure at the base. Because you have failed the material or you mobilize the material into a flow mechanism like this, where the full deep bearing capacity mechanism has to form, that is because I've driven the pile and unloaded it, so I've locked in quite a bit of my base resistance to the at the tip of the pile. Now, taking advantage of those two, they have proposed this QBO QC, mostly due to the work of Jardine and Chow. So again, linked to the displacement at the base, normalized to the diameter. And here, you also need this modulus, soil moduli, which is bit of a nuisance because A, we're not too confident in estimating the elastic modulus for a material that is going to flow like that. So it is a bit of a botch job. This is why there is still scope for research and everybody can have a go at this. There are still factors like this which we are not entirely happy with. We know what they mean and we can guess a value, but that doesn't mean that they are right. Also, the ratio between QB naught and QC is taken within a range of 0.3 to 0.7. So if I know my QC from the cone, I can estimate my QB for the pipe. Okay? That's basically the idea of all this. Now, this is back in, I don't know if I put the date here, this is back in mid-1990s. When Fiona Chow started her PhD, Jardine took her in a different direction, and he said, "Well, let's try and modify this QB and QC to make it more simple for everybody." And then they compared this with the other previous expressions, and they were almost the same. And this is much simpler expression where you're normalizing your base capacity with the cone tip resistance QC, and it only depends on the log function of the diameter of the pile to the diameter of the cone. Okay, so diameter of the rod of the cone. When I say diameter, and the expression I plotted here for convenience for a typical rod size, which is an inch, 25.4 millimeters, is what we popularly call an inch in England. All our measurements are still imperial. We just quote the equivalent SI units. So, if I now look at, let's play a little game. If we say that I'm going to have a 1 meter diameter pipe, then I can go up here, and that says QB or QC should be 0.2. So if I now measure QC, and so QB or QC is 0.2, that means QB must be 0.2 of my QC. Make sense? Now, if I now half the size of my pile, can go up here, and this ratio drops off. Because I'm multiplying with these things, it drops off more quickly. Okay, so you need more resistance to be mobilized at the pile base. So this is the one way of designing piles, at least for the base capacity. What about the skin friction? Skin friction, again, they proposed something slightly, uh, well, for driven piles, they have proposed this expression where your shear stress you're calculating based on effectively cone tip resistance divided by 45. These numbers are basically there to make the units work. So everything should work in SI units once you have these factors. Oops. One good thing they do is they take the vertical effective stress and normalize with the atmospheric pressure. So this PA here is basically 100 kP, which is 1 bar of atmospheric pressure. So you normalize your vertical stress with atmospheric pressure, so that becomes dimensionless. Also, you normalize the depth at which you are with the total height of the layer. So D over H is also dimensionless. And then you got these factors because they're fitting curves. Then you have this extra bit here. And this is interesting in that obviously as the soil, and we have some nice experiments on this done by a guy called Dave White. So professor at Southampton now. Suppose you are the soil here, and you are unfortunate enough to be in the line of the incoming pile. So the pile is coming towards you, and the guys above you will say, "Oh, this is calm, so we have to go there," right? And as the pile advances, you have to go away from the pile as well. In doing that, you tend to undergo shear deformation, and whenever you shear soil, you will undergo a volume change, unless you are at critical state, which is unlikely, because you are at a natural state to start. So, if I, you should always expect the soil at the base to be dilated, because it has to shear as the pile comes in. So, if the pile is then undergoing, or the soil is undergoing at the pile tip, this dilation, then that's going to change its stress state because the volume is changing, and therefore the contribution it can make to the skin friction. So by the time it came from here and launched itself here, according to setup mechanism, I'm in a different stress state compared to when I started here. Now we're going through all this detail because it's important to get the soil mechanics right. It's not just, oh, we'll multiply with the factor and hope for the best. This is really critical stuff. And that delta sigma dash RD is there to capture that dilation effect that happens in the soil. And delta CV, of course, is the friction angle between the interface between pile and soil. Again, there's a lot of research if you're interested to look at what this delta CV will be for sand, for clay, because where the shearing happens is not the same. You can get different claims. Now, Randolph obviously did not like that, and he proposed something different. So he came up with this expression that the shear stress can be estimated based on limiting earth pressure values effectively. So you have this K-min and K-max, and he is using an exponential decay. This is quite cool stuff because let me have some. This is why it is so clever. Everybody was focusing on how the material is flowing here. What Randolph did was to say, okay, if I take a plane along here, how far away will the soil know that that has been a part? Laterally, how far will the disturbance be felt by the soil? There obviously must be a boundary. I mean, if it is 10 diameters away or 20 diameters away from the pile, the soil doesn't know there is a pile that has been driven far away. Whereas next to the pile, of course, the soil will feel a hell lot of horizontal stress. So he basically said the horizontal, if I'm plotting horizontal stress along this axis, his assumption was that it will be highest here, some value, and it's going to decay exponentially. Okay? I bet you haven't read that in your textbooks. But it's common sense, isn't it? If you look at it, it must do that, surely. Uh, Whether it's exponential function or some logarithmic function, we can argue. Earlier, they were using logarithmic function, but this is exponential. But it must be of that nature. And then you have to make guesses about your K-min and K-max. So the K-max here is taken as proportional to QC, and which you normalize with your effective stress, and typically it will be about 1 or 2%. And K-min is taken in the range of 0.2 to 0.4 for particular types of for science. And again, mu we can take as 0.05. So this is a much easier expression to use and makes good use of QC and applies this decay, exponential decay idea we have in one go, in one equation. And this is obviously got him to give the Rankine lecture. If you do work like that, you can give the Rankine lecture, which by the way is our highest honor. It's like winning the Nobel Prize in geotechnical engineering is giving the Rankine lecture. Right. So we have looked at the base capacity and shaft capacity under static conditions using reasonably modern CPT testing. Of course, I haven't gone into details of clays and over-consolidation in clays and how do you estimate all that. If I did that, we have to name this just designing files under static conditions and run a course for that. We haven't got time for that. But what I suggest you do, especially if you're a student, is to, just like you printed my book online, go and print a copy of the Rankine lecture and go through that carefully. And also follow the references Randolph has used. It's about 15 years old or 10-year-old Rankine lecture now. And you should read, if you're in business of pile foundations, even remotely, you should read that and understand it. Okay? So please do that. And all the gaps I left for you can be filled by reading that. So he talks about, of course, the clays and soft clays, stiff clays and all that. I'm not going to do that. Other than that, any questions you have before I launch into dynamics? For some of you, it will be new, this way of thinking about pile foundations and designing pile foundations. And for senior staff, of course, they would have seen things like this before. But I thought I should include it nonetheless. Anything? Okay. let's begin at the very beginning, as I said. Typically, when there are piles in ground, and when we designed them to carry vertical load, like what we have discussed, and you are expecting earthquake loading on this, then two types of loading you should consider. The first one is the inertial loading. And in some ways, it is easier to work out the inertial loading on piles. And this is because, of course, the piles are carrying a structure on the top. Yes. So we are thinking of a case where we are shaking the base of the bedrock, and we are worried about the shear waves propagating upwards. And as they come, they can go through the pile. And when they come here, this bit will have some acceleration. And that, although we called it just V here, I'm sure Madam, the structural engineer, will object to that. And we actually have a column giving us that V. And so that's my pile. And the column is carrying the relay. This is the whole point of having a foundation, is that it's carrying a building, right? So when I shake this, the building will oscillate. And of course, it wants to slide and go away. And the pile won't let it do that, which means if I cut this here, like I have done there, I should get a big force because of the inertia, mass times acceleration. Yeah, so that is easy to see. So I got a big building sitting on the top, and that's trying to shake, and this is trying to stop or not allowing it to go away. So I must get a resisting shear force or inertial force. Typically, you call this base shear. And so the first effect of having an earthquake loading on the pile is that it has to sustain this additional horizontal loading induced by the inertia of the superstructure. So that's called the inertial load. So the pile cap wants to, the other way actually to look at this is the ground is all shaking, right? So even before the building sets off into motion, say the ground is doing in its first mode, shape like this. So that's the other way to look at it. So it's the incompatibility between what the building wants to do and what the ground wants to do. Is the way of another way of thinking about it. Then you got this other component called kinematic loading. Kinematic loading comes simply because the pile and the soil are not one and the same. They are different materials, different densities, and if the soil wants to do this and the pile wants to do something different, maybe it only wants to do this as a mode shape, there is this difference, right? So the soil wants to move more, the pile wants to move less, then the soil will slap the pile on either side in each half cycle. And that's inertial loading. It's very easy to understand. So not trickier to work out, but it's very easy to see where it comes from. But these two are known for ages now as the significant loads you've got to design your piles for. Because these are horizontal loads, they will induce a consequent shear force and bending moment. And you need to design the piles to carry this extra bending moment. Otherwise, you will get broken piles. Okay? And this is without any complication of liquefaction or anything. This is just piles going into ground and oscillate. When things don't go right, of course, things like this can happen. These are pictures from Taiwan, the Taichung earthquake 921, Chichi earthquake, it's called. And this is a very good example of inertial loading. Why? Because the bridge, the decks wanted to shake, the piers did not want to. The decks simply are too powerful, they're too heavy. So they basically pushed the pier and it ended up with piers like that. Okay? So the inertial loading from the superstructure was so great that the piers could not resist it. Of course, because it's a bridge, you've got the additional problem of having this at some height. So if I have a big horizontal force there, I'm also going to generate a moment, aren't I? So it's not just the fact that I have vertical horizontal load, but I also am applying a moment. So the pile head is being quite severely tested. Yeah? And in this case, of course, it failed the test. That's why it's on like that. The other issue, which I alluded to yesterday, is this issue of lateral sway. Where you got ground, I mean, you can see the river at the, of course, the bridges are always there because you want to cross the river. So the river is going to be there. And you have, because river carries water, the water table is always going to be shallow. Perfect conditions for liquefaction. And once the ground shakes, you can get the soil to move horizontally. And I've shown you other examples as well. The key thing here is this non-topid site is also close to the other one, and you can get extra kinematic loading because of the moving soil. Because liquefaction induced lateral spreading, and as the soil flows past the pile, it wants to take the pile with it. And here is a perfect example of that. The pier of the bridge standing in the way of soil. One thing as geotechnical engineers you must learn is never stand in the way of moving soil. It gets very cross. And the way it shows that is by applying passive pressures. If you allow it to move and then away from yourself, then it's quite benign because you'll only mobilize active pressures. But if you put stuff in its way, it gets cross. And the way it shows that is you can see how much the ground moved here. That's about 3/4 of a meter. And if you look carefully, you can see this soil piling behind the pier as well. And these piers were supported on single pile below. And again, that's a bad idea. And obviously, they have seen huge amounts of lateral loading because of the lateral spreading soil. So, inertial loading, we can imagine, if I draw cartoons of this, the columns will create base shear because of the inertial inertia of the building, and that is applied as a horizontal load onto the piles. Also, we said you can get a movement on top. Now, the failure mechanism immediately depends on how good your connection is between the pile cap and the piles. So, if you're a good structural engineer and carried the pile cap reinforcement properly to the piles and vice versa, it acts as one unit. That's good. On the other hand, if you chipped out on the connection, then of course you're asking for trouble. The other important thing, and this is slowly people are realizing this, is what we should stop designing these things as pile cap piles, geotech people, structure column, structural people. If you do that, when we are designing, we are ignoring some important things. For example, we could expect a pile cap like this to have hinges developing here because the cap itself is not allowed to rotate. Why? Because it has a column on the top and the column has the building on its head. So it's not easy for the pile cap to rotate. Whereas if I draw just the pile cap, I think, yeah, it can rotate. Why not? And that is why you've got to take the two together. On the other hand, if my pile cap is allowed to rotate, I'll get these hinges forming here, the plastic hinges. And if I prevent the rotation, the only other way the system can be formed is by bending the piles. Now, these two are not the same. Obviously, if you are designing for this case, you need reinforcement here because it is bending that way. Whereas if it does that, it's bending the other way. Completely different mechanisms on one simple thing. And I don't even need to do any tests to identify this. This is just me sitting down and imagining. Yeah, makes sense? So, inertial, the 2-3 things we quickly learned here are that the inertial loads are coming from the superstructure, but it's very important to know how these inertial loads are transferred onto the pile cap and therefore the piles, and what is the condition in which the pile cap will find itself. Is it going to be allowed to rotate or not rotate, and so on. You see that we are racking up the complexity of the problem quite quickly compared to doing just a pile design. So clearly, the amount of inertial loading depends on quite a few things. One is, of course, how big is the building on the top, the mass of the building. And the other thing is, how big is the earthquake we are designing for. And last but not the least is the soil characteristics. Because if my soil is very strong and won't let this bending to happen, then the failure will come somewhere else. Yeah. So obviously the soil strength has a big role to play. Here we are assuming the piles are going through soft soil and into stiff soil. But imagine it's the other way around. Then it will be different as well. Now, same idea with kinematic loading. So with kinematic loading, what we are saying is the free field displacements are going to be, let's say, assume like what I have drawn there here, which is a reasonable thing to say. You'll get almost no displacement at the base relative to the bedrock, by the way. And as you go up, you accumulate displacements because you've got more horizontal strains which you can integrate. So that's what, say, the free field is going to do. Now, the first case is as I said before, if the pile does not want to take the same shape, the mismatch between the two will cause horizontal loading. On top of that, if the soil wants to move more because it's on a slope and doing lateral spreading and so on, then it will impose even more kinematic loading. Yeah? So it all depends on the relative displacement of the soil between the soil and the pile. That's what induces your kinematic loads. There's one very important research area which is completely under researched at the moment is the link between inertial loading and kinematic loading. When I say the link, it's the phasing of the two loads. Do kinematic loads and inertial loads be applied at the same time on the pile, or will they happen at different times? With lateral spreading is a little bit easier because we know by the time the soil liquefies and starts spreading, the earthquake is finished, more or less. Which means by the time you mobilize your soil to go, the earthquake is finished. And therefore, the kinematic load imposed by the lateral spreading soil generally will be considered not in phase with the inertial loads. However, the shaking part of the inertial load, because the two things are shaking differently, can be in phase or out of phase. And there was very little work. One of the early people to look at that was Scott Vandenberg, Jim Davis, and a few others, but a lot is not known about this. So a conservative way would be to say, yeah, we'll pile it all on. But if you pile it all on, you're making your piles bigger, obviously. You're over designing piles. Now, the key design thing we all will be interested in this is the bending. And the reason I asked you to derive the scaling law for bending moment yesterday is because we will be doing, or I'll be showing the tests from the centrifuge testing, and I'll be quoting all the bending moments in prototype scale. But the ones we measure will be n cubed times small. Okay, but at least you know how that they are comparable to real structures. A few things, and I want to talk a little bit about this because a lot of people are talking about doing 1G testing as well. What is the key parameter for understanding the how the pile and the soil interact under dynamic conditions? So the way the inertial loading is going to act on the pile is going to be dependent on the relative stiffness of the pile with respect to soil. Now, we need a measure to determine this. So, we know just for the soil, yeah, the strength or stiffness will increase with depth. So, typically, if I'm plotting shear modulus or shear wave velocity, I expect to do that. And people like Gian and a lot of other people have got this. So we know my vertical stress and therefore my mean confining pressure increase linearly with that. Yeah. And the G is roughly a function of P dash to the power of half. And so it should be some kind of a parabola to with that. Okay. So that does not need much explanation. But what this does is this increasing stiffness trying to work out the this factor L, which is like working out an equivalent length, which depends on the diameter and the ratio of the modulus of the pile, Young's modulus of the pile, to the Young's modulus of soil. I absolutely, it hurts me to say Young's modulus of soil, because although there are books written on this and people, you probably don't find it so painful, but Young's modulus of soil does not make any sense. And this is part of the problem of dealing with this is all this nomenclature is coming from using elastic systems. And I've been showing time and time again these things are not elastic. The material behavior is not elastic. However, let's learn what other people are saying, and then we can go and cut them out. So this ratio EP Young's modulus of pile, I have no problem. In a way, I don't really care. It's structures, guys. You call them up and say, what's the Young's modulus of concrete or steel? They'll tell you. That's fine. It's not our problem. So EP I'm happy with. ES, Young's modulus of soil, the two things that are wrong with this, one is, first of all, it's Young's modulus, which we cannot measure properly anyhow. The other thing is, it's defined at a depth of the pile diameter. So what they want you to do is not only use this, but what is pile diameter? Maybe half a meter. So they want you to determine what the Young's modulus of the soil is at very shallow depth. Again, we know soils are fairly unreliable under very low confining stress. It hardly has anything to go by. So this comes from Eurocode 8, so and other codes as well. Why should I just the Europeans for this? But somehow the people who developed these expressions ran numerical analysis, and in computer code you can select Young's modulus wherever you like. So they said, oh, we'll select at one justification for this at all, other than that's somehow the early research has used that. Anyhow, that's where we are. But clearly having a ratio between the modulus of soil and modulus of the pile makes some sense. So that's the ratio. The power 0.22 is just a thing. And this 2 d naught is the diameter. Now you can define pile flexibility as this factor T, which depends on EI of the pile, which is its flexural stiffness. We are looking at horizontal vibration, so EI must play a role. And K is the mother of all fixes. It's called the soil modulus. So again, it's coming from the concept that we are having springs on this side, and we are saying, okay, let's try and have a go. And this is a very structural engineering approach to soil mechanics. To say that give us one number, and the one number will be K, because it's a spring constant. So the soil modulus normally people take is in the range of 200 to 2000 kilonewtons per cubic meter. If you have a range like that, 200 to 2000, that means you will pretty much get the answer you want by choosing the K properly, I should say. But forget calculating that, but you can see where the concept is. The concept is that you are comparing the stiffness of the soil to the stiffness of the pile in some way. And that is right. I have no problem with that. And once you have L and T, you can work out the so-called elastic length of pile. You can say it's winding me up already. This elastic length of pile is basically to tell you how long will the pile should be which interacts with in the vibrations. And that has some sense in it, although I may not work it this way. Clearly, if I have files that is long and shaking coming from here, or I have a file that is that long. If this bit is shaking the same, at some point the rest of the file doesn't matter. Or this bit here, although it is there, doesn't do anything. Yeah? Which means that we should be able to work out this active length or the elastic length of the file, which will participate with the vibrations. The concept sounds reasonable. The way we are working out may be completely foolish. Also, you can start seeing the flexibility of the file has the other benefit, which is if I work out my Z max here and it is greater than 5, then you can call this a flexible file. In other words, compared to the soil, the file will be easily movable. If, on the other hand, if Z max is less than 2.5, you can call it a rigid file. That is, it will not play ball and it will stay where it wants to be, and the soil has to deform around it. So these two, that's it. In ballpark terms, that's okay. We really know that the file behavior should be flexible or rigid depending on its stiffness related to that of the soil, which is what we worked out. Yeah? So, those are the limits. And whenever there are limits, there's always the zone between 2.5 and 5, and you call them semi-flexible. So the behavior will be somewhere between flexible and rigid. Yeah. This L and L are the same. You're just working the ratio. Now, this definition of flexibility is important because in terms of inertial loading, you can see if the files are classified as flexible or they will move, then you will attract all the shear load coming from the inertia of the building. The soil won't do anything for you because you're moving with the soil, and your pile has to carry the shear all the way down. So your shear forces are not going to be reduced because you're not mobilizing any interaction between the pile and the soil. However, so your inertial loads or the shear because of the inertial loads will be high. Yeah? But the benefit you get, on the other hand, is you have almost no kinematic loading. Because you're moving with the soil, you attract no kinematic loads. Yeah? I know I started the definition only half an hour ago, and now we are talking as if we are experts in inertial and kinematic loading, but run with me. But it makes sense, right? If the pile moves with the soil, there is no kinematic load, obviously. On the other hand, say this classification gave us rigid piles, or it classified our pile as rigid. Then you will attract huge amount of kinematic loads. Why? Because your pile is going to stay where it is. The whole soil wants to move with the earthquake, and the piles, you are hitting the pile constantly. So your kinematic loads increase enormously because of the passive pressures. And these kinematic loads then have to be added on as lateral load to your pile in carrying out your pile. So what we have done here is had a rough idea, quite foolishly and quite in ways I don't approve of. We worked out whether piles can be flexible or rigid, roughly. And at least that gives us an inkling of whether we should worry about the kinematic load or whether we should worry about the inertial loads. Okay? Now, let's worry a little bit more about what people are doing with the inertial load. Before we jump in, we need a definition. And this is quite an important definition. The kinematic interaction factor is defined as typically the ratio of the displacement of the pile head to the displacement of the soil. Now, I rubbed it out, but you have seen earlier, I was drawing these first mode shapes. That's my soil layer. You were saying that's the first mode for soil, and the pile may do smaller than that. So this is soil, and that is you remember I've drawn this earlier. What we're saying here is clearly a good measure of telling how much is the kinematic load is to say what is the ratio of that displacement to that displacement. Make sense? So one is the pile displacement is UP and that is U naught. Yeah? So UP or U naught gives you the interaction factor. Although I have drawn it that way, it is also possible, or you should be open to the possibility, that the pile head may displace more than the soil, because that depends on the dynamics. If you hit resonance in the pile, then the pile head may move more than the soil, then you will still get interaction, but it will be the other way. Because as the downside of kinematic interaction is, all you need is relative displacement between the pile and the soil. It doesn't matter which way it is. So it's either somebody slapping on your left cheek or right cheek. It still is a slap for you. Force of piles have nowhere to go. Okay? So IU is therefore defined as UP over U naught. And this is kind of become quite a standard way of defining interaction factors. Now, the next thing people do is to work out this dimensionless factor F, which brings in two things, interestingly. One is the previous friend we had, EP over ESD, which is the relative stiffness of the pile with respect to soil, with all my reservations about ESD. I'll put it out there, you already know that. And the ratio of the length of the pile to diameter of the pile. Again, that must be important because you can have short piles or long piles, right? So L over D to the power of minus half, EP over ESD to the power of 0.3. But one other important factor that we have brought in here is this F over Fn. So F over Fn is telling you whether the dynamics of the problem is important or not. Okay? So if my natural frequency of the system is kind of close to the driving frequency acquired by the earthquake, then this factor can become almost 1. Yeah, so this whole F factor becomes big. If my F is far away from natural frequency, then this ratio will be Right. So we are basically trying to get a response curve looking something like that. Okay. So that function will do that for you. Sorry, should I click? So it's like incorporating the resonance into the equation. Everybody happy with that? So at least people are trying to identify which are the important things that makes a difference in a fairly complicated problem. But then they fall into traps like this, where you have to work it out. You have to do sums, you have to do calculations. And IU therefore was, we defined IU and F, and this is how you link the two together. A horrendous equation, if I may say so. I didn't even have the heart to plot the damn thing. A times f to the power of 4, b times f to the power of 3, c times f squared plus 1 for some good reason is given as IQ. F, we understand. We're good with that. A, B, C are all fiddle factors. I can say more in the UK or in England, we are quite used to calling things what they are. Uh, Americans would probably will call them statistically based fit parameters or something. We will call them fiddle factors. Means if you want to fiddle the books or just get the calculation going but don't understand what's going on, we call them fiddle factors, right? So what would be an equivalent word you guys use here? Watch factors or what do you call it? Or maybe it depends on the local language. I can have some choice Telugu words for it. What do you call? You're being way too polite. There's nothing empirical about it. That's way too polite for my taste. So A, B, and C, you choose according to. There is a bit of logic to this in the whether you want to take the strength of the soil, whether it's going to increase or I should actually call it stiffness, right? Whether we are going to say it is going to be constant, linear, or a parallel. Okay, so those are the three options, and you can find these in literature, mostly work by gadgeters and people like that. So if it is constant, A and B become 0, you only have C, and if it's parabolic, those are the values, and if it's linear, another set of values. Again, people have basically done lots and lots of numerical analysis to work out those numbers. Nothing particularly holy about them. Right. I think I'm going to stop there before we show how well or not well these things work. Okay. Now, let's have some chat. What do you think of what you heard so far in terms of inertial and kinematic loading? Questions, discussion, points you want to make? Come on. I can't be the only one talking all the time. Any of you working on problems like this, where you are looking at file design, where with lateral loading from earthquakes and them? Yeah? Okay. So if you were to design these things, what would you consider? What are the main things? Can somebody, I've been speaking for an hour and a bit now. So what are the main things you learned? What is important? Kinematic or inertia? Or both or none? So I heard three answers. Both, kinematic, inertia. Nobody said none. Can you justify your
Most of the experiments say inertial load is detrimental than the lateral spreading of the flowing soil.
Yeah, that is true. We believe that. Can you see situations where the kinematic loads can dominate?
Like Elizabeth Mansell.
Liquefiable space.
Yeah, liquefiable soils are troublesome, but not so much just the liquefiable soil. Where you have lateral spreading with this non-liquefied crust on the top can create enormous loads. So that's one situation that kinematic loads can dominate. Also, think of the structure as well. As I said, don't think of just the piles, piles, piles. And, let's think of what they're carrying at the end of the day. If you have a structure which is quite light and flat, not high, right? So yeah, your inertial load then may be quite small from the building, whereas the kinematic loads are always going to be kinematic loads. So there are situations where the structure is, by virtue of its geometry, materials used, and so on, can be not contributing as much to the inertial load as you think it will. Plus the dynamics, whether the kinematic loads are in phase with the inertial loads is again going to be quite important. And I'm sure there'll be a lot more research that comes along to to clarify that. Yeah, good. Anything else people want to ask?
So which flow may be given either kinematic here either
Oh, yeah, yeah, sorry. Yeah,
either kinematic is dominating or inertial is dominating. Which will how we have to design why because of the
you need to decide. I mean, it depends on, as I said, the key players are the relative stiffness of the pile and the soil, the size of the building, mass of the building, all the structural detail. How much column shear do you expect from the building, structural dynamics of the building? Then you need to think of how big is the earthquake you're designing. So you need to know if the earthquake loading you're expecting is 0.3 G, zero point 0.4 G. Then the kinematic loading can become big because you're asking the soil to move a lot proportional to the input motion. And the pipes may not be able to do that because they have the building. It depends on working these three or four key things. And what I just showed is it will let you decide whether they fall under flexible or rigid, and then at least you can have a guess.
Can we relate the interaction of kinematic and inertial forces to the time period of soil and history?
Not natural frequency of the soil is very easy to work out. It's PS over 4H. So, but often that's not the highest response the soil does because it softens and it changes as the earthquake progresses. Uh, on top of that, you also so you got the time period of the soil changing all the time, part of the fun, and you got the building which does not change its period at all. You're trying to compare, put all of that together in one parameter. That's not possible. Okay. Yeah.
So these design procedures and everything, do they work for inclined files also, like for tall buildings when you have large lateral loads?
People obviously are designing them for all kinds of things, but the general wisdom is don't use battered files under earthquake loading because past case histories have shown quite a lot of damage for the battered files, especially key walls and port structures have battered files quite often because they get lateral loads, so they tend to put the files at an angle and they suffered quite badly. But that's just circumstantial evidence. I'm not aware of any. There are some few dodgy publications out there looking at this numerically, but if you want to study that, there are a few groups who are looking at them again to see whether there is any way we can design them. Usually they were failing at the connection between the pile and the pile head and the rest of the structure. So if we can design that better, maybe battered piles will work better. But as of now, if you ask any big company, saying, I want to design battered piles under Earth get very much. That word has got wrong, that they've did badly.
The failure pattern of files, it is possible to guess what type of loading.
Hmm. Yeah, definitely. And that's what Japanese are particularly good at it. After every earthquake, if the buildings fall down, or even sometimes when they're damaged significantly, they have to pull them down. They go and pull the piles out. So we have quite a nice array of information on where the cracks are in the piles they pulled out. So you can see whether it's damage because of lateral spreading, because of the was the damage at the pile head or piles buckled. I'll talk about that more in detail. But they're quite good at going and digging things up. I don't think we got one pile out of our Gujarat way, not one. But my worry is at completely different level. I remember uh, soon after the Gujarat earthquake, we all went on this site visit, about 8 of us engineers from the UK, and we saw quite a lot of damage, and of course, there were the bridges and so on. There was this one particular highway bridge, and the abutment walls moved in, and it wasn't even open; it's new. The earthquake happened before the open, and the decks came off, and the decks fell off. So I was talking to the site engineer. I said, "Oh, the abutments moved quite a lot. How are they founded to the beds?" And he said, "Oh, they're all pile foundations. They're going about 30 meters into them." And we kind of scratched our head, and I couldn't see how piles of the dimension he's talking about and the number of piles he's talking about could all fail at the pile head and allow the abutment wall to slide horizontally. Even if you use the poorest concrete quality you can imagine, they'll offer some resistance. And because the wall is so high and the bridge is high, you tend to get rotation. This one, yeah, it just slid horizontally. And I couldn't get the mechanics of it right. And it's a mystery. So you can't answer every question you say. A year later, there was some occasion I was coming to Bombay, and we took the time to go and see how Bhuj was recovering post earthquake, a year after the earthquake. We went to the same trip. Of course, they pulled the deck up and they're putting it back together. And this time, there was no site engineer. There was a very junior engineer. And I asked him, how did you guys fix those piles? They must have all been. He said, what piles? They never had any piles. Ah, right. And then he got out the drawings, and because he's junior, he knows how it works in the drawings. The site engineer who came when we first went was from head office. Maybe in his mind or in the design, actual design, they have design files. Nobody put them in that. So we are at a level where we need to worry whether we have files or not, let alone pulling them out after the earthquake. So we're in a totally different place. I'm sure things will improve. It's all quite new for us. A lot of this is very new for us. Whereas Japanese had earthquakes for 1,000 years and tsunamis for even longer. So they know the importance of studying that and the benefit, long-term benefit we get from it. Whereas in India, I think one thing we need to learn is the Gujarat earthquakes will happen once every 25, 30 years. It's long enough for people to forget and we'll do the same mistakes. But the more important things are to learn and apply many of these things to other major cities, Calcutta, Delhi, Northeast, all these are highly seismic and they get a lot more regular earthquakes. So there's a lot of benefit in understanding and designing this so that you don't need to constantly keep putting them back up again after they collapse. There is the human loss, but also there is infrastructure loss, which is very expensive to fix. The Bhuj earthquake costed the Indian economy, according to Unicredit or some insurer like that, about 30% of our GDP in one earthquake. And that's a lot. It's better to spend 2% of your GDP year on year and fix them properly. And then you have less casualties, less things to repair, and better confidence in the system. Okay, on the good thought, let's go for lunch. Some more questions? Okay.
I don't